Okay, this video, I'm going to go over section 4.7, exponential distribution. So in this video, let me use my lecture note. So because in this section, that there are lots of things to write it down. So let me use lecture note. So. Yep. Okay, so we're gonna study exponential distribution. So let me explain about exponential distribution, what it is, using this example. So couple wire. We haven't seen this example in Poisson distribution. So let x be the random variable denoting the length from any starting point on the wire until flow is detected. So then, in the Poisson distribution, the random variable x was defined as the number of flow, right? So, and that means in the Poisson distribution, the random variable was the discrete random variable, right? Excuse me. So, but here, we define the random variable x as the length. So it means that x is continuous random variable, right? And then the distribution of x can be obtained from knowledge of the distribution of the number of flow. So it means this. Now here the x, okay, this x is the what? The length, okay? So from any starting point on the wire until flow is detected, okay? So now then we can figure out the distribution of x from the random variable x in a Poisson distribution, which is number of flows. How? Here. Okay, let's see. The distance to the first flow exceed 3 millimeter. That means that there are no flow within a length of 3 millimeter. Does it make sense, right? So now, in general, let the random variable n denote the number of flows in x millimeter of wire. And if the mean number of flow is lambda per millimeter, then n has a Poisson distribution with a mean lambda x. Okay, so now here, what is n? N is what? N denote the what? Number of flow, right? Okay, in x millimeter. So n is nothing but the number of flows in x millimeter. So it means that n be considered as a random variable in Poisson distribution. Okay, so let's see. Oop. Okay, give me a second. All right, so now then, so we know the PMF, probability mass function of Poisson distribution, and then there's a CMF, right? So probability x is greater than x is equal to, this is, keep in mind is that x is what? The length, okay? So this x is a random variable of exponential distribution, and the n, that's the random variable in a Poisson distribution. Keep in mind this. So probability x is greater than x means that there will be no flow until x millimeter. It means that n equals 0. So probability x is greater than x means the probability that the length, the until we got flow is greater than x is equal to probability the number of the flow is 0 within x millimeter. Okay, this is a Poisson distribution. Okay, so applying the PMF, probability mass function of Poisson distribution. Okay, then we're gonna get this e to the negative lambda x. All right, but what is this? This is what? Probability x is greater than x. This is CDF, right? Cumulative density function. So this is nothing but f of x. We can write it down, right? And then now, oh, sorry. This is the I'm sorry, this is 1 minus CDF. I'm sorry, this is equal to 1. Oops, here. Okay, so let's see. So this one, this is equal to, what is equal to 1 minus probably that. Yeah. Wow, always really hard. X is what? Less than or equals X, right? Okay. So the other way, then the probability that X is less than or equal X, that's the what? F of X. Okay. So F of X is this, and this is equal to 1 minus e to negative lambda. So we can say that, right? Definitely X is must be greater than equal to 0. Why? Because X represents length. Okay. So now then, we want to find out CDF. Okay. So we got PDF. Sorry. So we got CDF, right? We know the relationship between CDF and PDF. So derivative of CDF is going to be PDF. So using that, we take a derivative of this guy, then we're going to get this. That's going to be PDF of the exponential distribution. Okay. So let's see, and then now, let's see, next one is this one. Okay. Now, oh, sorry. Okay. All right. So now, next one. Give me a second. All right. Fully understand this is a little bit blurry. Okay. So now, the derivation of the distribution of x depends only on the assumption that the flows in the wire follow a Poisson process. Yep. And then the starting point for measuring x does not matter because the probability of number of flows in an interval of Poisson process depends only on the length of the interval, not on the location. Yeah, so not on the location. So you understood that? So let's see example, let's see example 4.17. Okay, so oh, yeah, just please look at this one by yourself. Okay, let me skip that example. All right, so this is just a read. I'm sure that you could understand by reading that example. Okay, now then we go, we see, we define the exponential distribution. So random variable x, give me a second. So the random variable x, that equals the distance between the successive event from a Poisson process with the mean number of events lambda, and then unit interval is on exponential random variable with the parameter lambda. So what is x? X, that equals the distance between successive event from a Poisson process. Okay, and then the lambda is the mean number of event. Okay, then the PDF of x is going to be this, and the mean going to be 1 over lambda, and then variance is going to be 1 over lambda square. All right. And now look at the example for 4.17. So let's see. Okay. Let me see. Okay, so 4.17. Yeah, so let me see. Yep. Okay. All right, so in a large corporate computer network, user logons to the system can be modeled as a Poisson process with a mean of 25 logons per hour. Yeah, so then we see 25 is what? The lambda, right? Then what is the probability that there are no logons in an interval of 6 minutes? So this is the value, specific value of random variable, right? So this is going to be x, right? This is lambda, right? So now then, let x the time in hours from the start of the interval until the first log on. Yep. Yeah, we define x like that. And then x has an exponential distribution with lambda 25. And then we are we are interested in the probability that x exceeds 6 minutes. Okay, because lambda is given in logons per hour, we express all time unit in our, I mean, we have to unify the unit, time unit, right? So 6 minutes must be what? 6 over 60 hours, which is 0.1 hour, right? Okay. So we divide 6 by 60 because to unify the time unit to hour. Okay. Then probability that the what? X exceeds 6 minutes, which is x is greater than 0.1, right? Is equal to integral 0.1 through infinity, and then the lambda times e to negative lambda x. Let's see. So what? Give me a second. Oh. Give me a second. Something wrong. Yep. Okay, I fixed it. All right. So now then, it's not a big deal to evaluate the integral, right? Because just use the you can use a u substitution, but since you see e to negative 25x, this is a linear function, so you don't have to use u substitution. Okay, so because the integer of this guy, e to the negative 25x, is going to be 1 over negative 25 times e to negative 25x. All right, so and then applying the fundamental theorem calculus part 2. So we're going to do this. Okay. So now then the cumulative CDF can also be used to obtain the same result as follows. So probability x is greater than 0.1 is equal to 1 minus probability x is less than or equals 0.1. Okay. So then what? This is going to be, that should be equal to e to the negative lambda x. Okay. You got it? Okay. So now, an identical answer is obtained by expressing the mean number of logons as 0.417 logons per excuse me, minute. So where that number comes from? Yeah, so we convert the mean number of logons per hour to mean number of logons per minute. So we divide 625 by excuse me 60. Okay. So now then, computing the probability that the time until the next log one exceeds the 6 minute. Give me a second. All right, I'm sorry. Okay, so now time until the next log one exceeds 6 minutes. All right, let me try. And then what is the probability that the time until the next log one is between 2 and 3 minutes? So we have to figure out, we have to change the what? Give me a second. Let's see. So now here, give me a second. Let me see right here. So before, to figure out the answer for that question, okay, what is the probability that the time until next logon is between 2 and 3 minutes? Let's try. I mean, let's figure out this one. I mean, let's try to figure out the probability. I mean, we should get the same answer as this one. I mean, 0.082, even though we use the minute as a time unit. Okay, so probability that what x is x is greater than 6. Okay, x is greater than 6 is equal to what, integral 6 to infinity, isn't it? And then not 25 but 0.417. Does it make sense? And then times e to the negative 0.417x dx. Okay, you can use this. You can say that 0.417 and then e to the minus 0.417 okay, and then x dx. Okay, so now then let's see the next question. So it means this question means what? We need to calculate probability the x is between 2 minute and 3 minute, but we gotta just convert the 2 minute 3 minute to hour, right? So 2 minute is 0.033 hours and 3 minute is 0.05 hours. Okay, and then we evaluate that integral. Yeah. Now next one, let's see. Oh, okay. Oh, where is one? Yeah, and the alternative solution. So yeah, also we can figure out this one by using CDF. Okay, so I'm not going to explain this in detail. Okay, I'm sure that you can figure out this. Okay, and then let's see, then determine the interval of time such that probability that no log one occur in the interval is 0.9. It means that we got to find out specific variable, the random variable where the PD, I mean, the probability is 0.90. Okay, so probability x is greater than x. You see that? Determine the number of times such the probability that no log one occurs in the number. Okay, no log one occur. It means in the number. Then what? The question asked for the length of time x such that probability that x is greater than x is 0.990. Okay. So what's the x? X is the what? The length, right? It's in this case the time interval. So let me see the time interval in. The time. Probability that of random variable. Time is greater than x means that after a certain time interval, no log one occur is 0.90. Means that probability that random variable x is exceed a certain time x, lowercase x, is equal to 0.9. Okay, so take the now how can you solve this? Yeah, we just take a natural log on both sides, right? Because this is a exponential equation, so I'm sure that you can solve this equation. So just take a natural log on both sides and isolate x, then you will get this. Okay, let me tell you again. Take a natural log right here. Just say it right. Take a natural log, okay, and then negative. We can take out negative 25x out of natural log, and then isolate x. Then you should get this one. Okay, and then mean gonna be 1 over lambda, which is 0.04, right? And then sigma gonna be also 1 over lambda. Okay, so now next one is see example 4.18. So not this one. By the way, in the black in a Blackboard, you see what I'll post the lecture video link right there. Okay, So whenever I just record a lecture video lecture, and then I'll post in upload in a YouTube, and then I post the YouTube link in the Blackboard. Okay. So now the share screen and not this one. Okay. So next one is a lack of memory property. So lack of memory property is this. Probability that lack of memory property is related to the conditional probability. Okay. So conditional probability that x is less than t1 plus t2. T1 is a timing number. T2 is another timing number. Given that x is greater than t1 is equal to probability that x is less than t2. Okay. So this is one of property in a exponential distribution. So please look at this one. What? Oh, give me a second. So what does that mean? Sorry. So should be on this one. Yeah. Oh. Okay. So then. So just take a look at this figure, okay? So this one, and let's say this is, let's say this is T2, and this is T1, and T1 plus T2. Yeah, it makes sense. And then we want to figure out the conditional probability that x is less than T1 plus T2, given that x is greater than T1. Okay. Then using the definition of the conditional probability, we're going to get this. Probability that x is between t1 and t1 plus t2 over probability that x is greater than t1, right? And then, yeah, we know the definition of the PDF of exponential distribution, which is integral and then t1 and t1 plus t2 and lambda times e to negative lambda x. Okay. Over and then integral t1 through infinity, blah, blah, blah. You see? So what does that mean in calculus? That integral t1 through t1 plus t2 times lambda times e to the negative lambda x. That is nothing but, by the way, what's the graph? What's the function of this graph? The f of x, right? Okay. So what's the definition of f of x? Lambda times e to the negative lambda x. Okay. So that integral from t1 through t1 plus t2 t1 f of x and lambda times e to the negative lambda x, we can say this one as f of x, right? So that means the area C, okay, t1 through t1 plus 2, and then the area, that's going to be area t1 plus C over, and then t1 integral t1 to infinity e lambda times e to negative lambda. Right? That's nothing but the area C and D, right? Okay. So probability x is less than t2 is equal to also, the lack of memory says that this is equal to probability that x is less than t2, right? So let's figure out probability x is less than t2. This is going to be 0 to t2 lambda times e to lambda t. The integral of lambda times e to negative lambda from 0 to t2, okay? Excuse me. So, and then keep in mind this. So now, this is area of A, right? Area of A. Okay. So pretty much we can say that the area of C over the area C and D is equal to the is equal to the area of A. Okay. So that's the geometric explanation, geometrical explanation of the lack of memory property. Okay. So now, mm, excuse me. Think. Yeah, I think I did go over all examples and just contents in 4.7. Okay, let me stop here. In the next video, I'm going to go over 4.8. Thank you.